Afternoon. This next one, using a mobile phone as a 2D virtual tracing tool, static peephole versus magic lens. And I confess I knew nothing whatsoever about this topic, so we'll be very interested to see what it involves. So, thank you.
Okay. So, a warm and sunny hello from our office in University of Primorska. As said, I will be presenting the work in relation to virtual tracing, which is actually a mobile phone system that lets you transcribe digital information to physical objects. The work I'm presenting is the work we did in collaboration with my colleague Matjaž Kljun and Paul Colton from University of Lancaster. So let's start with looking at the motivation for our work. The motivation comes from the fact that there are many people who like to create different things and make things with their hands. So these people create all sorts of things, like paintings, but all sorts of paintings, not just what we usually are used to. They also like to sew their own clothes, or, for example, build models from balsa wood, such as houses, or planes, for example. And the common problem in all these activities is that in this process of making things, they regularly need to complete the task of transcribing information from one object to another. So if you look at an example of making a model plane, you get a miniature, you get a design plan, a blueprint, and you need to actually transcribe information from this blueprint to a piece of wood that you cut and create a model from. Similar problem occurs also when you try to sew a piece of clothing, for example. In this case, you need to cut the fabric of the material prior to sewing. So again, you have the problem of actually transferring the patterns from the clothing, from the plan to the fabric itself, so you can cut it. Or for example, if you think about painting, you are not a very skilled painter. You actually can use existing designs to set out correct perspectives and proportions for your drawing plan. And again, you need to transcribe this kind of information. In all these activities, the creators actually transcribe information from one object to another. And they've done this for quite a while. So there are many ways of doing that. And in the next couple of slides, I will talk about these ways of how people can achieve this thing. And the basic concept, the simplest way, if you are a skilled artist, you don't need any tool. You just basically observe the scene and actually transcribe information based on observations to a new layer of material. Okay, that's okay when you are creating an artistic element, but if your product is actually dependent on the correct size of the end result, for example, in clothing, it's very important that it fits you well, so you need to actually create the product of exact size. Then this process of transcribing information is not very useful. So there is an alternative. And an alternative to this is actually to use template technique, which actually works by placing a template below a semi-transparent material, and then you can actually trace draw on the semi-transparent material the design that's below the template. Or if the material is not transparent, you can actually place indigo paper below the template and place indigo paper and template onto this layer of material that you want to actually transcribe the information to. And at the places where you exert pressure, actually the indigo paper leaves the mark on the underlying surface. So basically you use the template to follow your design, and as you follow the design, you exert pressure at different places, and this pressure to indigo goes down to your underlying surface. So that's the template approach. very common one. An alternative to template approach is to use a stencil. So basically here you cut out pieces of template material, and now you have the edges of this material, and you can actually follow the edges to transcribe again information to this new layer. In this case, you see an example of transcribing to fabric the design of clothing you want to. So the problem of both of these methods is that you actually need to produce such templates and stencils, and this can be time-consuming, difficult, and also limited, especially if you think about larger formats. So, for example, just think about how difficult it is to print large format papers. We don't have A0 printers at home that wait for our impulse of creating something. So what we propose here in this research is we look at an alternative solution to this problem. We call this solution virtual tracing using virtual templates. And what is virtual tracing? It's actually a method for transcribing instructions from virtual templates that are shown on mobile device screen. And we transcribe this instruction also on any underlying surface. So the mobile device renders a virtual template image. In this case of this image, this is the red colored contour of a cartoon character. And beside that red contour, you can also see a live video stream of the drawing surface. You can see that on the screen of the phone, you just manage to spot the pen of the person on the drawing surface. And just by matching the position of the pen and the contour, the person can actually transcribe this information to the underlying surface. Okay, so that's virtual tracing. So let's now look on how we actually evaluate and build the prototypes and actually conduct our research in this method. So the evaluation is done by comparing three different methods of transcribing information from one object to another. And these three interfaces are the traditional template interface, which is the one we've seen before, where you put a template and a semi-transparent surface over it, and then you can trace draw on the new layer the instructions from below. And then we had the other two, and then we had another two methods which are both virtual tracing methods. The first one is called static peephole virtual tracing, and the last one is called augmented reality magic lens. So the core challenge, okay, there are some obvious advantages of using virtual tracing instead of standard techniques. And the clear advantage is sort of the one that I already mentioned, which is that you don't have to physically produce the sketching aids tools in order to transcribe your information, which is particularly problematic when you are working with large formats. In case of virtual tracing, that's not a problem, because we all know that actually in digital world the size is not a problem. The only thing that comes here is that if you want to draw designs which are larger than the field of view of the camera on a mobile phone, then you need to move the camera, move the phone itself to progress through the design. So you basically what you do is you draw small segments of the design, but with this kind of technique you can draw anything as big as you want. Basically, there's theoretically no limit to the size of the drawing you can create with this kind of method. But the core challenge in this virtual tracing is actually how do you manage to align the virtual template with what has been drawn this far, and how can you do that? That's now the challenge. In case of static peephole interaction mode, the user has to do this manually. And how this works is actually an image. You have the phone. You put the phone on the stand, and you start drawing the template on the underlying surface. And as soon as you move the phone, of course, the virtual template doesn't match up with what has been drawn this far. So you need to use touchscreen gestures to position virtual template to the correct segment so that you can actually continue drawing what hasn't been drawn this far. So you do this kind of manual alignment. In case of Magic Lens mode, you don't have to do these kind of things because we use automatic alignment for that. Magic Lens is actually a paradigm which is most common example of augmented reality interface. And the way it works is the camera actually, you track the position of the camera in relation to the drawing surface. And if you know the position of the camera in relation to the drawing surface, you can always project the virtual template so that it matches with what has been drawn this far. So you can map the projection to the design that you've drawn this far. So you don't need to manually align this anymore. I've got a short video of this prototype, and I think it's a good time to just quickly have a look at that. Hope I won't have problems starting it up. Okay. I hope you can see that. So here you see a person holding the phone, and on the phone screen you can see in red color the virtual template, and the person using the pen just follows, as he sees the pen on the screen, he can follow the contour. And this is not speeded up image, that's the speed our participants, this is actually a real footage from the study itself. So that's this. I hope you managed to capture this. So let's move on. Okay, so we got these three modes. We've seen, we know what template is, we know what static peephole is, the manual adjustment, and now we saw the short demo of Magic Lens. And for the Magic Lens interface, there's an important thing about our prototype that I have to mention. And this is the marker. You can see that we have to place an artificial marker into the drawing surface in order to be able to implement this kind of Magic Lens interface. And the problem comes from the fact that it is actually almost impossible to track the position of the camera phone on a blank sheet of paper. So you have to introduce certain features, certain elements inside in order to be able to achieve this kind of automatic alignment of what has been drawn and the virtual template. And this is actually potentially a problem because it may affect the drawing experience. Because now the user has to handle this marker, which is in some situations obstructing him from drawing a segment of the painting, so he has to actually work around that, and the system only works as long as the marker is visible in the scene. So this is one potential problem. And the second potential problem with virtual tracing is that the fact that the person has to look through the phone when he creates the design. So he has to actually be able to look through the phone and follow the instructions. There is a problem of depth. You know, if you look through a camera which is only one, you don't have correct depth perception. So you might have problems figuring out when you're going to touch the surface and start drawing prior to when you want it. And the second problem comes from the fact that actually you have this marker, which is actually something you might not like. And all these things open up some interesting questions, which we set out to answer in our research. And the first thing we want to see is basically how effective are phones in supporting user sketching through virtual tracing. Can people do it? How well can they do it? How fast can they do it? And how does this compare to traditional sketching aids? The second thing we wanted to look at is to see if users find the advantage of Magic Lens useful. So if this technology, as it is today, actually helps users in coming with finished results. this is an interesting question because there's quite a lot of previous research which compares magic lens interface and static peephole interface. And none of this research finds magic lens interface particularly useful, which is a downside for augmented reality because there's a lot of effort involved in creating solutions that can actually implement magic lens interaction. So a lot of effort usually means a lot of money, usually means a lot of processing powers on your phone. So it has to be better in order to make it a successful product. If we move on to the next part, which is actually the interesting point for us was also to figure out, can actually people hold the device in their hand when they actually transcribe this information? Because we know that in case of virtual tracing with static peephole, you need a stand in order to transcribe information because users manually align the virtual temple with the real world. In case of magic lens, the alignment is done automatically, and that happens on every camera frame. So even though you move the phone, you shake the phone, the contour still stays at the correct place, so you can continue drawing. So theoretically, it should be possible to draw whilst holding the device in hand, and that's important. That's an important advantage if you think about real-world applications. You don't need a stand; you can sketch something without actually preparing to sketch. You have your mobile phone available at your hand, so you can actually start to use the technology without prior setting. Let's move on and look at how we went to actually evaluate this kind of system. So to answer these questions, we designed a user study, and this study asked participants to complete an unfinished cartoon character, and this is what they get on the. You can see on the picture on the left what was this unfinished character, and this was actually a drawing of A3 size. So they have to finish that using different tracing techniques. The first technique was the one that I described before, template. The second one was static peephole virtual tracing, and the third one was magic lens mode. We had in total 7 participants from 23 to 45 years old. 3 were employed, 4 were students. All came from various backgrounds, such as architecture, computer science, medicine, mechanical engineering, and do we have somebody else? So I don't, and that's it. So they came from mixed backgrounds. And we asked participants to complete this task as quickly as possible, and each participant completed 3 drawings, so each drawing in its own method. Okay, so let's move on to results. Okay, first to data collection. So what kind of data did we collect as participants completed this task? First of all, we collected drawings that were created by participants. We also collected task time completion and gave participants quiz questionnaires after each interaction. So we could actually get an overall reaction to our prototype, an estimate of reaction to our prototype. We also, at the end of the questionnaires, we also had some open-ended questions which asked participants to rank interaction modes and justify their decision. And also, we asked them to highlight the most difficult part of the task itself. So, as you can see, we predominantly focused on qualitative data collection methods, mainly because we had a small sample size, and also, yeah, that's the main reason. And this is also the reason why, as I'm going to go through results, we only show descriptive statistic results. So we didn't go into statistical analysis because the sample size is too small to make, so this doesn't make sense. So how did we judge quality? Okay, we did that by ranking the 3 drawings produced by each participant from best to worst, and two researchers did that. So for each participant, we had a score, and we didn't know when we were ranking these paintings, drawings, we didn't know which one was made with which interface. So actually, we should be able to spot what's better and what's worse And as you see the results on the right, it's not very obvious that one method produces a much better result than another. Okay, we can see an indication of template method being the most accurate one, the one that produces the best results, but there is not a lot of difference between peephole and magic lens interaction mode. And what this allows us to conclude is that it is possible to use mobile phones for virtual tracing, as obviously the quality rank shows that they've achieved similar kind of level of performance. It also shows that virtual tracing whilst holding the phone in hand is possible. We can say this because magic lens mode actually performed even better than peephole, even though the difference is very small. So people were able to hold the phone whilst sketching and were actually as good as when they were using static peephole interaction mode, meaning that the phone was actually on the stand. So these are the first two conclusions. So if we move on to time, in time it becomes more obvious the difference between the interaction modes. Especially here you can see that the traditional template mode is for sure the fastest mode. And maybe the quality of the drawing was a bit lower because the people were actually drawing this painting so fast, these sketches so fast. However, you again see the same trend as observed in previous slide. There is not a lot of difference between peephole and magic lens. Again, this allows us to conclude that users are very good at manually aligning virtual content with what has been drawn this far. Why can we say this? Because in static peephole mode, users have to manually align the contour every time they move the phone, and they had to move the phone because the format of the drawing was bigger than what they could capture with the camera of the phone. So they were actually, this result indicates that they were actually very good at manually aligning this virtual content, because in magic lens, where they didn't have to align this manually, they weren't much faster. Again, this also indirectly suggests that automatic alignment using marker is not good enough. So our prototype, where we had the magic lens, which required the marker, is not a good enough solution for this kind of action. So let's move on to quiz results. Okay, this is the questionnaire result. We're sort of trying to guess what kind of user satisfaction was there when they were using prototypes. And again, it shows the same trend. Template got the highest score, and then peephole, magic lens very close together. So again, supporting our previous conclusions. When we, at the end of the questionnaire, we also asked people to rank the interaction modes and ask them sort of question which interaction mode would you use now if you would be faced with the same task. And again, most people selected template mode, and there is not a lot of difference between the other two. So again, in line with results from previous slides. Beside these results, we also have some observational results which are quite interesting. First is that the distance from the phone to the drawing surface was always within this bound of 17 to 22 centimeters. This is interesting because you could actually move further away from the desk and get a wider view of the drawing surface, but then it would be difficult for you to actually do the drawing because the screen is close to you and your hand is far away, so it creates this problem. And the second thing, so this suggests that just moving the phone away from the drawing surface is not the solution of the problem. And the second thing is when drawing participants always looked at the paper through the phone, keeping the pencil within the camera's field of view. What I mean by that is, even though you were positioned at a certain segment and you had to connect your design with what has been drawn this far, and this design was actually outside the viewfinder of your phone, you did not cross this border. You always went with the phone to that border. And this was also true in case of manual alignment. So you moved the phone before you actually finished up the drawing. The third thing that we've observed is that participants look at the paper to see how they were progressing. What does this mean is that actually virtual templates are projected over the existing designs. Even though this virtual template, this red contour line, was semi-transparent, it actually occluded what participants drew with pencil. So they weren't sure which segments of the drawing they finished already. So this is a limitation that could be fixed in the future, so that actually only the instructions that haven't been transcribed are actually those that are shown to the user. So that's what we observed. And lastly, there was this thing that static peak call interaction always forced our participants to draw all instructions within the screen segment. What does this mean is that they move the phone only after they've completed every little bit of the drawing. And this wasn't the case in Magic Lens mode. They never went to the very edge of the device. They always sort of moved the device and drew as they were progressing. Also, another static peak call mode observation was that participants expressed the need for a minimap. Basically, what they were looking for was a feature that would allow them to get a wider context of the drawing. So they were sort of, let's say, a little bit lost when they were sort of moving around with the phone. So they would need some sort of minimap that would help them navigate to the whole drawing surface. And again, this was only spotted in case of static peak or interaction mode. So what are the conclusions? It's possible we conclude that it's possible to use mobile phones for virtual tracing, although traditional methods continue to be quicker. We say that virtual tracing while holding the phone in hand is possible. And perhaps the most significant one is that Magic Lens only achieved comparable performance to static peak call mode. So again, Magic Lens didn't manage to outperform this more simple, basic interaction mode. And we can conclude that from users' dislike of the marker, which was expressed through open-ended questions, we can see that actually the currently available tracking solutions are not good enough, so they would need some sort of improvement. So what do we want to do in the future? First, look into ways of detecting what has been drawn this far, so that we only draw the parts of instructions that haven't been visible this far. We want to run a user study with more participants, as I said, not conclusive in terms of statistical analysis. We want to explore the use of a stand in the context of Magic Lens. We had here this ambiguity that in static peak call we use the stand, whereas in Magic Lens interaction we did not use the stand. So that's something that might have affected our results. We also want to evaluate virtual tracing using virtual mirror metaphor. This is an example is Osmo Play, which is a commercial application that actually lets you use your iPad as a mirror, and you've seen the mirror design and your hand on the design and sort of transcribe information in this way. And lastly, we want to look into ways of supporting transcribing, into supporting transcription of 3D information to objects which are also three-dimensional, such as try to see if this kind of technology can be used for in terms of sculpturing aids. So I think I'm at the end. Thank you for your time. I hope I wasn't too long. If you have some questions or comments, please come forward.
Well, thank you very much for that. We have time for 2 or 3 quick questions.
I don't have to shout. What are the general things that you have learned about designing user interfaces from this? I know there's a whole bunch of particular details, but what can I walk away with that will help me design user interfaces in the future?
Okay, thank you for the question. The first thing is, if you are planning to do some sort of system where you plan to transcribe information from digital to physical, you definitely should not use augmented reality interface if you cannot implement tracking without adding artificial markers. So your system has to be able to deal with camera pose tracking without additional markers in the scene. Otherwise, if you can't do that, if you're not capable of implementing such solution, it's better to use static peephole interaction mode, basically meaning that you actually have a stand and place the device on the stand as you transcribe information. And as you implement such solution, add to such solution this kind of, minimap. So a context element, a context feature that will let users understand where on the picture they are. Because we said we are drawing small segments of the picture, and using a context map, we would know at what segment we are. So it would help us, it would guide us in this context, in this wider context. So this is the second one. And the third one is what we've observed is that usually, because people had, the users had this stand height adjustable, so they could adjust the height up to 35 centimeters. So from the desk. But what they actually did is they kept it quite close to the drawing surface. So what you could summarize from this is that the stand you design doesn't have to be that high. It's actually closed down that the interaction actually happens. And of course, if you have the money and if you have the know-how of implementing this kind of interface where only segments of the scene are, where the virtual template only shows undrawn segments of the scene, that's definitely something you should look after. I hope I answered your question.
Right, well, I think we're out of time, so thank you very much for the presentation of an extremely interesting topic. Thank you.